Hi, I'm Nick and I'm working with Neil, and we're going to tell you about enhanced geothermal systems. Here's a quick video to kind of get you on the right track.
Jr., and I'd like to tell you about an exciting new renewable energy technology. Altarock Energy is conducting the Newberry Volcano Enhanced Geothermal Systems demonstration in the Deschutes National Forest in Central Oregon. First, I'd like to tell you a little about the history of geothermal energy and how this new technology, enhanced geothermal systems, can dramatically increase the use of geothermal energy and help secure our nation's energy independence. Geothermal energy, the Earth's own heat, could help solve today's energy challenges. Geothermal power generation dates back to 1904, when at the Larderello geothermal field in Italy, electricity was generated from geothermal energy for the first time. Geothermal energy is already being used today for domestic heating and electricity production, providing clean, renewable baseload power. It could contribute to a sustainable energy future for the United States and around the world. Geothermal power represents an essentially unlimited resource we can more fully develop and dynamically change our energy future. So what do we need to do to take advantage of this tremendous resource potential? Naturally occurring geothermal systems, called hydrothermal reservoirs, are only found where heat and open fractures filled with water can be accessed at relatively shallow depths, like in the western U.S. and around the Ring of Fire. What if we could create ideal geothermal conditions almost anywhere? That's exactly what Enhanced Geothermal Systems, or EGS, proposes to do. To help us fully understand EGS, let's first look at how a natural hydrothermal system works. In a naturally occurring hydrothermal system, groundwater is heated by underlying magma or by circulation through deep faults or fissures. Production wells, drilled into the Earth's surface, tap into the hot fluid of these naturally occurring hydrothermal reservoirs. Under pressure, heated fluid flows up these production wells to the surface and into a power plant. Geothermal energy gives us a reliable flow of renewable baseload power with minimal environmental impact. Remember though, naturally occurring geothermal does have its limitations. It can only be used where underground reservoirs naturally exist, mostly in the western United States. EGS, however, can be created almost anywhere. By creating a water-filled fracture network in hot rock, we can make a geothermal reservoir. EGS could be a viable solution to the energy challenges facing us today and to the creation of a new energy economy. Let's look at a current EGS project, the Newberry EGS.
So we're going to go into more depth about the Newberry volcano project later during our case study.
So, to begin, for a geothermal resource to be viable for power generation, 4 conditions must be met. There must be an existence of sufficient heat, the availability of sufficient fluid to transfer heat from subsurface to power generation equipment, adequate permeability to allow sufficient mass of fluid to circulate through geothermal reservoirs at a rate high enough to achieve reasonable power outputs, and sufficient stability to allow sustainable power generation. Starting with sufficient heat for EGS systems, theoretically, the minimum temperature for current geothermal power generation equipment is roughly 95 degrees Celsius. In actuality though, the minimum temperature varies depending on the temperature at the back end of the power generation cycle. In order to generate enough power for a geothermal system to be viable, there must be enough fluid to allow for heat to transfer to the generator equipment through the fluid. If a geothermal site lacks the water required for this, other fluids such as brine or seawater and CO2 can be utilized. In order to obtain adequate permeability for an enhanced geothermal system, the interconnected porosity of the medium through which mass will flow should be high enough to achieve flow rates of approximately 10 kilograms per second. This is only the theoretical flow rate required, however. More extensive analysis must take place in a real-world setting, as a higher flow rate may be required for power generation to be viable. For an enhanced geothermal system to be viable, it must also exhibit sufficient stability. Stability in this case refers to the rated lifetime of the power generation facility. The lifetime of these facilities should be roughly 20 years at minimum. However, the goal should be to maximize the possible lifetime of this facility in order to increase revenue while driving down cost of maintenance and repair. Another factor to consider when creating an enhanced geothermal system is resource size. I have a quote here from William Glassley. Over the last decade, sufficient technological progress has been made so that previously unusable thermal reservoirs can begin to be considered for useful power generation. The viability of a location for geothermal power generation involves considering the amount of energy available in 1 kilometer cubed of rock that is at elevated temperature. Here, I have attached a photo of current geothermal reservoirs across America. Areas highlighted in red, mostly in the Nevada, Utah, Oregon, and Washington regions, will produce the most amount of geothermal energy, while orange areas are also viable for direct use of heated fluid in geothermal systems, albeit at a lower power generation rate. Areas in peach denote where fluids must be heated further for utilization in geothermal systems. As a continuation of resource size for enhanced geothermal systems, the amount of energy that can be extracted is a function of the heat capacity of the rock, the number of degrees by which the temperatures decrease during power generation, and the density of the rock and rock volume. There is an equation here which I have posted, where QEX is the possible energy extracted in an area, V is the volume of rock, P is the density of the rock, and delta T is the change in temperature during power generation. In reference to resource size, here are a few more quotes that I found from William Glassley. It has been estimated that down to a depth of 10 kilometers in the subsurface of the United States, there is a thermal energy resource base in excess of 13 million exajoules, where 1 exajoule equals 1,018 joules. Though only 1.5% of this resource can be extracted by current technology, roughly about 200,000 exajoules, it represents more than 2,000 times the amount of energy consumed by the United States. Now we'll be getting on to some characteristics of enhanced geothermal systems. In most deeper regions of the subsurface, where temperatures are in excess of 150 degrees Celsius, there is insufficient natural porosity and permeability to accommodate significant mass flow of fluid. To access fluids from these subsurfaces, the porosity and permeability of a volume of rock must be increased through stimulation. Stimulation involves either hydroshearing or hydrofracturing. Once stimulated, other wells can be drilled into the stimulated zone to create a flow pathway for other fluids in non-stimulated areas. To identify candidate zones for stimulation, one method that is used to note the depth intervals at which circulation of drilling muds are lost during drilling. By mapping these zones of lost circulation during drilling, it is possible to locate those regions of medium to high permeability that exist naturally in the geological system. The highest permeability zones offer access to the best thermal regimes for geothermal power. Another method for detecting where flow may occur is to map temperature perturbations in boreholes when a well is drilled and monitored. One methodology for doing this is called distributed temperature sensing. In a DTS system, fiber optic cables are enclosed within a high-grade steel tube a few millimeters in diameter. The cable is then suspended across the entire length of the borehole. By using sophisticated detection equipment and processing algorithms, the temperature of the DTS cable can be determined everywhere across the length in virtual real time. The primary limitation of DTS systems, however, is their survivability at high temperatures. Permeability enhancement is accomplished by developing a network of fractures that provide access for fluids to extract heat from a sufficiently large rock volume. The most effective way to accomplish this is by injecting fluids at pressures that are high enough to induce brittle failure of existing fractures or intact rock. A method that has been recently developed for isolating zones of stimulation avoids the use of mechanical devices to block off segments of the borehole, and instead uses materials to plug existing fracture networks or permeability zones. These materials are called thermally degradable zonal isolation materials. TZIM material will rapidly break down under the conditions that are observed in the region that is in the stimulation target, but will persist for longer to block those regions for which stimulation is not desired due to its lower temperature. Now, I'm going to hand it off to Nick to continue onwards.
EGS system development. Attempts to develop EGS began in the late 70s and early 80s in New Mexico with the Fenton Hill Hot Dry Rock Project. This was the first project to undertake deep drilling, stimulation, and fluid injection. So as you can see, these projects aren't quite as exciting as the typical geothermal power plants that we've been looking at. They're not, usually located on hot spots. Occasionally they're located on volcanoes, but other than that, they just look like your typical. So here are some locations and characteristics of EGS sites worldwide. Although only the site in Germany is a successful commercial enterprise that provides power to the grid, many other projects have been successful in initial test. In the United States, the Nevada and Oregon sites have both completed initial development and test phases, and I'll go into more depth in the Oregon site in my case study. Drilling and downhole equipment. Drill bits and pipe that are used for EGS are often identical to the equipment used in oil and gas drilling, which don't encounter as severe of conditions. High temperatures and pressures associated with EGS make stimulating and completing a well particularly difficult. Equipment failure of downhole sensing equipment, Packards, and other electronic devices is common. This is important because downhole cameras and such devices are used to map fractures before starting the stimulation process. So a really important factor regarding EGS systems is reservoir management and sustainability. Conduction is the dominant heat transfer mechanism, and convection plays a very minor role in EGS sites. When EGS development takes place in these settings, convection-dominated heat transfer is introduced into the reservoir when the reservoir is stimulated and fluid is pumped through the fracture system. Because heat transfer by convection occurs at a rate that is much faster than the conduction rate, heat will be removed faster than it is actually replaced. Thus, the challenge is how to best manage the resource and ensure that it can sustain power production over the lifetime of the power generating facility. Here's an equation we can use to tell how much time it will take for a reservoir to recover. This approach is kind of a bit more basic approach. It assumes constant temperatures on either side of the reservoir body and does not account for change in conductivity with temperature. But estimating the time that a reservoir takes to recover is a really complicated process, and it requires a lot of knowledge of the geometry of the reservoir and a lot of other factors that this equation doesn't necessarily account for. Alright, now we're moving on to our case study, and we're covering the Newberry volcano, which is a EGS development in Oregon. So it's located next to abundance of volcanoes, and unlike the volcanoes that it surrounds, which are stratovolcanoes, Newberry is a shield volcano that has been dormant for about 1,300 years now. And here's a video that will cover it a little bit.
Energy economy. Let's look at a current EGS project, the Newberry EGS demonstration being conducted by Altarock in the Deschutes National Forest in Central Oregon. In Phase 1, a team of scientists and engineers review existing data about the Newberry EGS demonstration site, conduct baseline measurements, develop plans, and obtain permits for Phase 2 operations. In Phase 2, We will create an EGS reservoir around an existing well, over 10,000 feet deep, using Alturoc's proprietary methods and technology. By injecting water at high pressure, we will open or stimulate existing natural fractures using a process called hydro-shearing. Clean, cold groundwater, produced from an existing on-site shallow water well, is pumped at high pressure deep into the injection well, where the temperature is over 600 degrees Fahrenheit. When the cold water reaches the hot, dry rock surrounding the well bore, the injection pressure causes the existing natural fractures to open and fill with water. This process is continued until cracks are opened to a distance of about 1,500 feet, or 500 meters, around the well bore. When the first fracture system has grown to the desired size, a biodegradable, non-toxic material called a diverter is injected with the water to temporarily block fluid flow into the newly opened fractures. The diverter forms a shield around the well bore in the first set of fractures, so more fractures can be opened deeper in the well bore. As the diverter begins to block the first set of fractures, continued water injection causes a second fracture system to open, followed by a second injection of diverter, shielding the second fracture system from further stimulation. We use this to control the size of the reservoir as it forms. A third cold water injection creates the final fracture system, and the stimulation process is complete. At this point, the water injection is stopped and the injected water begins to reheat. As the water heats, the biodegradable diverter begins to dissolve, allowing the fractures to open and the water to flow through the entire fracture network. The hydro-shearing process and opening of cracks creates movement and sound in the rock, resulting in microseismicity. The opening and growth of fractures during stimulation is mapped by real-time measurement of this microseismicity. Using a microseismic array and AltiStim, Alturoc's sophisticated proprietary modeling software, we can closely monitor the process. We'll map the fracture network and generate a microseismic event map around the well bore, showing us the size, location, and orientation of the fracture system. With all this information, we know where to drill the production wells into the fracture network. Conventional well drilling techniques are used to directionally drill production wells into the newly created EGS reservoir. Precision-guided directional drilling allows us to penetrate the greatest number of open fractures for maximum well productivity. Cold water can now be pumped down the injection well, flowing through the newly created EGS fracture network, absorbing heat and flowing up and out of the production wells, creating hot water or steam to generate electricity or provide domestic heating. In Phase 3 of the Newberry EGS demonstration, we summarize the collected information to develop a conceptual model of a commercial-scale EGS system, including the most cost-effective way to create an EGS reservoir, the performance that can be expected, the number of wells required, and the best type of power generation technology to use, either flash or binary. While not part of the Newberry EGS demonstration, electricity can be generated from geothermal energy using one of two power cycles, flash or binary.
That stuff's kind of already been covered. So the Newberry plant was stimulated in 3 stages. The first stage was done using only water, and the second 2 stages involved this TZIM product, which is the blocker that it was talking about. And over the course of this 3-phase stimulation period, it was about 7 weeks, and they injected over 41,000 cubic meters of water. But during the stimulation process, the Newberry EGS plant experienced some difficulties. The main one being when they were trying to stimulate it, the TZIM would seal the shallower fractures, but as it got deeper, it would quickly dissolve and it wouldn't allow the 3 stages to allow pressure to build up, so it basically just dissolve and hydro shear, and they couldn't penetrate the deepest part of, they couldn't hydro shear the deepest part of the well, which they were trying to do.